Okay, this is our last arena laboratory, our last laboratory experience for 475, Lab 10, Arena 6, where we're going to round out a few more advanced concepts in Arena, as well as give you opportunities to work with some additional tools in the kind of Arena software suite that make simulation and simulation optimization a little easier. So this is broken into two parts. We're going to have a manufacturing system model in the first part that's actually going to build off of a model that you used in Lab 9, and you'll do a few modifications to it. And then we'll have a batch processing model in Model 9.4, the second part of this lab, that is actually very similar to the kind of muffin baking sim that we saw in Lab 2, but it's implemented in Arena and has a little bit more realism added to it. Now, the main points for this lab all come from Part 1. Part 2, so Part 1 will be worth 30 points, and Part 2 will be worth 20 points. And so the lab is totally out of 30. So it's almost like you get 2/3 of a bonus lab if you complete both parts of this. All right, so that's all we're saying here, 30 points plus the 20-point bonus, due at the normal time though. I'm expecting you to submit a Word document, and if you can, it'd also be helpful you to submit that PDF version that helps us in the grading. And then there will be two model files, one for that first part and the other for the second part. And in that Word document, there'll be answers to a number of questions. And I really do mean answers, discussion. I want you to show that you aren't just reporting data from the models, that you're interpreting that data. So if you're doing this in the lab, then your goal is to basically complete the modifications to generate a working model for Part 1. If you can do that, then I'm pretty sure that you can go home and work on the discussion part. So Part 1, a small manufacturing system. So we are mainly going to cover these things called sequences, these more advanced uses of sets. Now we've already seen resource sets in the cross-training example from the call center. And so here we'll see sets used in a more general way. And then we'll see how variables can be indexed, and that allows for you to more compactly specify parameter or things that change in your model that that may vary with, say, an entity type or something along those lines. And so it allows you to get rid of some of the ugly decision logic and end up bundling things inside a data structure, so it kind of simplifies your model diagram. So hopefully that will become clear as you work through this model. So again, there's going to be some questions that you'll submit in this Word document as well as this modified model. So we've provided you the model 7.1, which was again the same model that you started working with in Lab 9. So you'll start with that. But what I want you to do is to go and look through section 7.1 through section 7.15, including that last visualization section from section 7.15 from your Kelton textbook. So if take a look at that and familiarize yourself with the way this manufacturing system model works, with the station transfers, specifically with how sequences work. And so there's sequences and sets. So I will, what this model looks like, I'll toggle over to Arena, is this thing here. So again, you might recognize this from last time. Let me see if my mouse is working. And if it is not, then let me back out of PowerPoint so that we can just look at this model here. So this here is the small manufacturing system, model 7.1. And in the small manufacturing system, it has all these station transfers. So parts arrive, and then they hit this start sequence, which will end up sending them off to these different stations. And in the major new thing here is if you go into the advanced transfer panel here, and this is the important one, then you'll notice this sequence data module. And under the sequence data module, then we'll see, there are 3 different sequences. So if I drill down, let's see, into the sequence called Part 2 Process Plan, if I drill into that, then I see that this has multiple steps. And so then if I then drill down into the first step in this sequence, Cell 1, Part 2, Step 1, Then I click into that and I see that it says the station associated this with is cell 1, and we have a step name, part 2, step 1. And there's no assignments, but you could put assignments here that would occur during this step. And we'll see that in some of the rest of these. So like if I go to cell 2, part 2, step 2, then what this is saying is that this step in the sequence is going to take me to the cell 2 station, but before it does that, it is going to assign onto an attribute a process time from a triangular distribution. So the idea here is that we are going to have these parts, which you'll see through the logic that's described in the book. Parts will get created. Some of these parts will be of part 2. Those part 2 parts, when they hit this start sequence block, then they will reference this sequence here, and it will go to the part 2 process plan. And that part 2 process plan means that the first step in the sequence will be to go down here to cell 1, and we'll go into this cell 1 process. We'll end up being delayed by that cell 1 process time. And then it will finish and go back into this kind of start sequence block, where it will then move on to the next step in that sequence, which is this cell 2. And in cell 2, before it goes into that, it assigns the process time from this triangular distribution, and then it goes to this cell 2 station, and then that cell 2 process, it will be delayed by this process time that just got assigned. And once it's done, it will then route from cell 2 back to the sequence, and then that will then go to the next step. So part 2, parts of type 2 will end up going down through all of these steps in the sequence. So this is a way, so basically what these sequences allow you to do is build modules of your system and not worry about the routing between the modules, because now you can actually have parts being routed in different sequences from module to module based on their part type. And that is what the major advantage here is how to make use of these sequences so that maybe parts of type 1, when they get created, maybe they visit cell 1, then cell 3, then cell 1, then cell 2, and then exit. But parts of type 2, maybe they go 1, 3, 2, 4, 1, 3, and then exit. And so the sequences allow you to make a list of the steps and then have different entities follow different lists without having to upset your model logic here. And if we were to hit run, then the other nice thing about this is they implemented this really nice visualization here. And so if I were to try to slow this down any farther, then I can see, maybe pause, that I've got parts that maybe we'll do a couple of steps here. So I can see that I have parts of different types. Right now, all I can see is type 2 parts. But eventually, oh, there's a type 3. So I can see that I've got type 2 parts and type 3 parts, and if I were to watch them move around, then they would visit these stations in different orders because they have different sequences. They have part-specific sequences. And so that is what you're experimenting with this model. All right, so let's go back to the PowerPoint here. And so that is a brief overview of this Model 7.1. So what I'm going to want you to do is to then go into Model 7.1. Sorry about that. And there's a current way that the cell 1 process delays are implemented is not making full use of this sequencing like the rest are. So I want you to read through section 7.1 and pay special attention to sections 7.1.3 and 7.1.4 to find out how sequences work. And I want you to modify the cell 1 process to be a little bit like the cell 2, cell 3, and cell 4 processes, where the entity attributes are assigned within the sequence. And so there's going to be an entity attribute called process time. And that process time will get assigned within the sequence. And then the cell 1 process block will end up using that attribute to decide how long to wait. And that's the way it's done in the other cells. But the way the book has written it just to show a diversity of way of doing things is they have not done that for the cell 1 process. And so I want you to go in and take the book suggestion and use the sequences to update that cell 1 process. And so when you're done with that, then I want you to submit your modified DOE file with your Canvas submission. I want you to have images of the flowchart, but the flowchart's going to look roughly the same, and that's why I also want to see modified sequence steps in your Word document there. So don't only just show me the flowchart, which should be right out of the model, but also then show me a screenshot or capture of, or at least describe to me how you changed the sequencing for these parts so that the process delay for cell 1 in this manufacturing system are actually assigned within the sequence as opposed to being assigned inside the cell 1 process. All right, so then I want you to answer a few questions in your Word document. So how would you model sequence-dependent transfer times? Right now, the transfer times are constant. How might you say for this sequence we'll have these transfer times and for this other sequence we'll have a different transfer time? Why would you want to do it that way? It might be that for parts of a particular type, when they go through their sequence, maybe they can't move as quickly from one to the other because they're just more massive parts. Something along those lines. Or maybe you want to better modify that when you move from cell 1 to cell 3, that transfer time is going to be longer than moving from cell 1 to cell 2. And so I'm asking, how would you use sequences to implement these sequence-dependent transfer times? Then we're going to go back to basically what you did in Lab 9, and I want you to run a 5-day simulation with 15 replications and find the average and 95% confidence interval of the total WIP. And so if you remember from Lab 9, in order for you to get a good steady state average, you need to set up a warm-up period. And so I want you to then use what you learned in Lab 9 to set up this warm-up period, and then so that your average isn't biased by this warm-up period as this WIP warms up. All right, so look back at Lab 9 for how to build the total WIP output statistic and how to deal with this warm-up stuff. Then explain in your own words the arena logic required to make the machines in cell 3 process have different machine-specific delays. And so if you read the book, you'll see what I mean by that. But basically, what we're going to say is that in cell 3, there's 2 types of machines, and some machines work faster than others, and they have a way to choose which machine you're going to use. And so how, in your own words, summarize how that's been implemented in Arena. And then the fourth question here, right now there is a certain part distribution. So there's a certain fraction of part 1 parts, part 2 parts, and part 3 parts that come through the system, even though there is only one create block. So if we look back here, we see it just says create parts on the left there. And so the question is, how is this distribution being maintained? How is it implemented? And how would you go in and change it to be 10% of part type 1, 20% of part type 2, and the rest part type 3. All right, so that was the end of the first part. So those are all the regulation points. If you do the first part and you get it all right, then you've got 100% on the lab. If you want to do a little more, because this is the last lab of the semester, and you just want to learn a little bit more about Arena and about the simulation modeling, then I encourage you to take on the bonus part. So this second part here is purely bonus. It's got 20 points possible. That's another whole 2/3 of a lab that are being added on if you get all this right. And it goes over batching, these cool features in Arena, signals and holds, and a little bit of how to make use of OptQuest in the Process Analyzer. I'm expecting you, if you choose to do this one, to submit, add your results to the Lab10 doc file or PDF as well. So that's going to be an image of your model that you built and a response to these prompts, and then also upload the model that you built. So what is this model that we're building? So you follow the instructions in section 9.4 to build something which looks like, let's see if I have to back on a PowerPoint here for a second. So you'll end up building this model 9.4 that looks like this. And this is very similar, again, to the muffin baking simulation. So we're going to get arrivals, and those arrivals have to wait for a while until, and if I drill down into this hold for signal, then we'll see that it waits for a signal, and so there is going to be a signal that is sent in the rest of this simulation. So down here, when it says signal for batch release, then basically when an entity pushes through here, this will unleash these entities that have been waiting here. So entities come in, they wait for it to be released by this signal down here, and then they go into this batch icon here, where basically it takes all of those entities and it creates batches of batch size, and this is a variable that you can change. It is a decision variable. How big should this batch size be? So again, this should feel a lot like the muffin baking simulation, where you had to wait for a certain number of muffins to accumulate before you could put them in the oven. So then they'll be delayed, and after the delay, you record how many were processed. So you can think of this like the oven in the muffin baking simulation. How long are they delayed? How long is a batch delayed? Then you record how many got actually processed, and then you decide whether it is time to leave the oven warm or to make the oven cool down or turn off, given that when you need to turn the oven back on, it's going to take it a certain amount of time, let's say 8 minutes, to warm back up again. And so this logic down here is the logic for deciding based on how many things are waiting. So if I look at this wait queue less than, it's looking at the number of items that are sitting in this hold for signal queue. And it is saying that based on the conditions in here, it's determining how many of these muffins do we need to wait for before we flip that oven back on in the simulation. So and so there's basically, you're going to find that there's going to be a logic here that is kind of going to sandwich the number of muffins in this queue between this number and another number that you specify here. And so that will end up being what this logic is all about, is sort of, do I keep the oven on? Do I spin it down? And when I spin it down, when do I spin it back up and pay the cost of turning that oven back on? So all of this is outlined in that book section, but I'm just sort of giving you a rough idea of what this, like this here is where the kind of oven is happening. And then down here, this is sort of the restart logic for when do we keep the oven on and let it keep running, or when do we turn the oven off and then wait for it to be turned back on, in which case we have to wait for it to warm back up before we can then run batches through it again. So that is a rough outline of this Model 9.4. And so my tips for you as you're building it, because you will build it from scratch here, is to make sure you set the time units to minutes everywhere throughout the model, in run setup, etc. The batch model is in the basic process panel, so that's easy to find. If you're looking for the signal and hold modules, they're over in the advanced process panel. So if I go into here, basic process, then I will find batch right there. But signal and hold, those are under advanced process. So there's hold right there and signal down here. And if you missed it the last time in the previous model, advanced transfer, that's where that sequence is. But there's no sequencing in this model. Okay, so just other things that I can point out here. The delay for process block has an expression for its delay. So I've said, 3 plus 0.06 times batch size. Well, that's over here. 3 plus 0.06 times batch size. And I want you to think about what's going on there. Why is there this variable batch size in there in this delay for process? What is that doing? Okay. So then you'll notice these expressions, min and inq, are going to show up. So if I look at this wait queue less than, I see this inq. That means number in the queue. So remember, if I go to build expression, if I looked under queuing and then I looked under current number in the queue, then that is what this in queue is. So that is the current number that are in whatever queue is in the parentheses here. So in this case, the hold for signal queue, so here's hold for signal and here's its queue. These are how many entities are currently waiting in the queue. If I look back at the PowerPoint here, then I see MN, this minimum value. And so there's a number of in queue there. Let's see. I'm trying to remember where the MN is. Right here. So under assign batch size, then I see this function, the minimum value between the number that are currently in this queue and this variable max batch. So basically this whole thing is either going to be max batch or the current number that are in the queue. It will take the smallest of the two. So that's what that MN stands for there. And again, if I were to go to build expression and if I were looked under math functions, then I should be able to find minimum value, and then it's that MN, and it shows you whatever its arguments are, it will take the minimum of the comma separated arguments. So that's what's going on there. All right, any other tips that I want to point out here? The delay for 8 minutes takes a constant expression, so make sure this is set to constant, value 8, and again, minutes everywhere. And the max batch value statistic should be of type output. So we talk about this match batch value. Well, remember statistics are under the advanced process panel. If I go down to statistic, then I've got this max batch value that I'll need to put in there. And when I click on that, it is of type output. And not only does it type output, but then we have this funny little expression here. So let's unpack this a little bit. So type output means that at every replication, it's going to take the current value of whatever this expression is, and it will report that just for that replication. So if you run 15 replications, then each replication will have one number associated with it for this output. Now, Dmax, so you might not remember, it's easy to forget what these Dmax things are. Now what this is, if I look in my build expression under statistic, and I go under time persistent, and then I go to max value, then I see that there's this Dmax, and this Dmax is applied to this so-called dstat. Now what that's all about is there is this hold for signal.q, which is just the queue that's above the hold for signal here, and then its number in queue. And this is one of these time persistent statistics. And what that basically means is the number in queue is a count which is accumulating continuously over time. And so that's what we mean by time persistent. It persists over time. It is a long time series. And so at the end of a replication, we can then ask questions about that time series. We can take the average over time, for example, of that time series. In this case, we're taking the maximum over time. So this is a time persistent statistic over this. This is a statistic over time for this time persistent data. And so that Dmax will end up being, let's say it's 35. Well, that will mean sometime during the replication, there were 35 entities waiting right here. And so that's what this max batch value is going to bring out for us. Okay. So so you'll build all this thing, and you'll end up making sure you follow all these tips. And you'll move forward, and then now I want you to work with this model that you just built. And so what I want you to do is to choose 3 different pairs of values for the variables restart and max batch. I'm not referring to max batch value, that output. I'm referring to these variables. So if I again go back into here, and I go to basic process, and I go down to variable down here, then I see that there are variables restart and max batch, as well as batch size. Now, batch size is something that is used during the runtime. It's being kind of edited by these things. Notice that there's an assigned batch size here. But these variables are parameters. These are decision variables that we end up setting once before we run the simulation and letting the simulation go. If I look at their initial values, then I can see, and I can either do that by clicking on this initial values, or I think I could just right click on this and say edit via dialog. And I can see that max batch in this case has an initial value of 10, and over here restart has an initial value of 6. And so what I'm asking you to do in these PowerPoint instructions here is to choose 3 different pairs of restart and max batch, and you'll need to go through and figure out what the meaning of restart and max batch are. Choose 3 different valid pairs of those, and then study those 3 pairs to see which ones is the best policy. And so those are the questions I'm asking you. How does the number of restarts compare across the 3 combinations you choose? So when I say number of restarts, I'm referring to the counter here, record startups. So how many times does this, what does this counter read? So this is an output, this counter, whereas these variables restart, this is an input. So I am referring to the number of restarts. What is the count of oven restarts if we're using this as an oven simulation? How does that compare across the 3 combinations? And I don't want you to just say that, oh, my first combination had a lower number than my second combination. I want you to try to make an attempt to explain the relationship. Why do you think there were more restarts for one combination than another? Now, near the end of section 9.4.2, so if you flip open this textbook, and if you were to go all the way to section 9.5 and then flip back, so somewhere under, say, display 915, there is a paragraph that comments on this max batch value statistic that we've already talked about, this output statistic. And it measures the performance of this system in terms of this kind of queue here. And so I'm asking, what is the max batch value corresponding to the restart max batch pair that you found? So you optimize this pair over the number of restarts. And I'm saying for the one that minimized the number of restarts, I guess I would say, so for the one that minimized the number of restarts, what is the value of the other output max batch value? In other words, is there sort of a tension between these two? If you reduce the number of restarts, do you end up also increasing or decreasing or something like that, this max batch value? Now, the book discusses using OptQuest, and I'll show you about how to use Process Analyzer and OptQuest for this one in just a second. But they just sort of say, hypothetically speaking, if you were to use OptQuest with a constraint that max batch value to be no more than 25, then I'm saying, based off that discussion, if your manager comes up to you and asks you about your simulation model and how it works, I'm asking you to explain to your manager, in other words, explain in lay terms, what does this max batch value statistic, the output, not the max batch variable, but the max batch value output statistic, what does it represent? What is the meaning of this? And then, is there going to this trade-off language, can you explain to your manager why there might be a risk that a policy with a low number of restarts might also have a large max batch value statistic? So in other words, if you can manage to optimize the policy so that you don't have to restart the oven a whole lot, then what cost is that in terms of these other performance variables? So what might we accidentally do in trying to just reduce the number of restarts? Okay, now a couple other questions to wrap out this bonus, and that's, recall the muffin baking simulation that I've already referred to a couple of times from Lab 2. Think about how Model 9.4 could be modified to implement the muffin baking simulation that you did by hand in Lab 2. So for example, if we look back here, then because our muffin oven doesn't restart, then we might need to get rid of this whole restart logic right here. So we're never going to turn the muffin oven off, so we're never going to have to turn it back on and wait for it to come back on. Now there's also this wait queue less than 2 block, which again routes it out to this restart. So if you get rid of all the restart logic, then you basically have something that is almost ready to implement the muffin baking simulation. But it's not quite there. So I say discuss some other ways this model should be rearranged in order to model the muffin baking oven. So specifically, how should the create arrivals block up here be changed? So without giving any answers away, then I'm just saying that how the time between arrivals and the entities per arrival that show up in this create arrivals block. So there's a time between arrivals as well as entities per arrival. So time between arrivals, that's this, entities per arrival. If I wanted to go back to Lab 2, then I would need to modify those. They need to both change. And the entities per arrival needs to be a UNIF expression. So if I were to go to the entities per arrival and go to build expression, then UNIF, well, that actually comes right out of this these random distributions here. And so you notice there is a UNIF right here. Oh, that's just the uniform random variable, which has a minimum value and a maximum value. And so my claim here is that the entities per arrival could be this UNIF expression. That is one way that we can model that. But so just go back and look at Lab 2 and think about that. And if you're thinking about this, entities per arrival, remember it sounds kind of discrete, but UNIF is continuous. So what are different ways that we can deal with that? All right, so then using terms from the muffin bake scenario of Lab 2, then interpret what does the max batch variable represent? And what does the restart variable represent? So we already used things in the Lab 2 example that are related to max batch and restart. And so what did we call that in Lab 2? So how do we map the Lab 2 simulation model onto the implementation in this arena model? So what would max batch here represent there? What would restart here represent there? That's what I want you to explain. And otherwise, that's all for this Lab 10. I mentioned to you that I will show you how to use the Process Analyzer and OptQuest to simplify these simulation optimization cases like this. Since this video has already gone on for a half hour, I'm going to stop this video here and we'll do a part 2 where we go into using Process Analyzer and OptQuest for models like these.